Okay, so yeah, good. Thanks. So here is the lecture 3 of Mathematical Foundation of Generative AI. In today's lecture, we're going to talk about the famous paper DDPM, denoising diffusion probabilistic models. It's being proposed, and so the paper was out 2020. After 4 years, it has more than 12,000 citations, which is quite impressive. So nowadays already. So this has been really a hot topic in the past couple of years. Usually these kind of concepts and materials are not really right in the textbook. So it's quite like still under like at a research level. There are a lot of things. There are some level of mathematical justification, but some of this is still very ad hoc. So they still have a lot of things can be and digging out to do some research with that, and a lot of interesting things still coming out in the day by days. So okay, so let's get back to this. So I want to picture everything in terms of images. For example, my x0 is called image. So the main philosophy is I want to gradually tear down these images into the white noises. Right? Oh, and like a way of thinking is you have, say, if you give a bunch of Lego blocks to the kids that is only 5 years old, for example, my daughter, and she don't know how to build this and the Lego and the blocks to be a buildings, because usually this is a very hard job for 5-year-old kids. So a way to think about this is if you give the building built by Legos and tear down one by one and show to my daughter and go back to and show the back and how to be built up. And she might like gradually to learn how to build up and the Legos. So this is the rough philosophy of things. In human beings, it's very easy to tear down something is well structured. It is extraordinarily difficult to rebuild something from noises into some meaningful things. So this is, and the thing is, the inverse part from like something like each blocks, like Lego blocks back to the buildings, that step by step could be learned from the deep learning part. So the whole idea is we have images here. At the end, I want to get something like white noises. So you can think this is being a Z here. But I'm going to gradually tear down these images a bit by bit. For example, this is my x1, my x2, and then dot to xt minus 1. Right. So basically, and you want to tear down this so images one by one. And like eventually it becomes a white noise. So this part is called tearing. But say if we gradually tear down, so we know say x1 and x2. So like basically x2 is more close to the white noise compared to the x1. So and hypothetically we can use these intermediate steps to rebuild. And for this part, I'm using a slightly different color here. This part is we can use those intermediate steps to rebuild.
To what word? To do what? Rebuild.
Okay. Yeah, rebuild. Okay. So, and in terms of models, so as everything will be quite similar to VAE that we talked about, but VAE we need to decide on what is the hidden dimensions and what is a lot of and a lot of parameters need to be tuned. Here, our I view the models according to this the whole idea. If we can tear things down, then then basically here we are getting like Q of x1, Q of x0. So basically we are building the models. If you are given of x0 and my tearing down process can give the probability of x1s and so on. So you have basically the Q of X of T, conditional on Xt minus 1. And like all like intermediate probabilities. So here I call it Q here. The other one I'm gonna call it P. But although it's called P and Q, but they're also and being and similar to and the same as probabilities. So this is probability of X0 given of X1 and the probability of Xt minus 1 given of Xt. And so all quantity of P and Q are unknown. In particularly, we are going to use some function form to approximate both of this. For example, if you are given like one specific set of xt, this xt plus 1, this is xt minus 1. So you know as t like progress, this image is gradually and getting close to a white noise. All right, so we know this one, it's q of xt, conditional of xt minus 1. Here, this way, it's p of xt, conditional of xt minus 1. And of course, we never know both of this. I'm going to approximate by a parameterized family. We're going to specify later. And the same here, we're going to approximate by the parameterized family. Like that. Okay. In particularly, we need to know, and these are my parameter, which is phi and v. In this case, and this is very similar to BAE in the general framework, but the architecture will be significantly different. And particularly, we have the process of the tiering. So, so what is the tiering down part? So the simplest tiering down part is gradually adding the white noises. So, and here is my assumption here. I assume I tier my images down with the following form. So this is all element-wise. So basically, if you have the image of 1 million pixels, for each pixels, you are going to process element-wise. And this, and epsilon follows the Gaussian distributions, standard Gaussian. And so here we just do like 1D things, and of course you can and apply to like and multiple dimensions, but like and each dimension will be an independent. Then in particular, the transition probability which is my q phi of xt, condition of xt minus 1. So basically, if you know xt minus 1, the xt will follows a Gaussian distribution. This is xt of random variable. The mean will be alpha t, xt minus 1. The standard deviation will be 1 minus alpha t. Okay, so this is very simple exercises from the univariate and the regression problem. So the question is, why we have to set this way, right? And usually you think about this, so and basically you are like and times some constant at each xt minus 1. plus some noises. Why this constant has to be related to the noises that I'm going to, and the variances of the noises that I want to and apply to. So this is the question. Why? Yeah.
What is that symbol inside the square root? Or what is it?
I mean, this is alpha t. So alpha.
Okay.
Yeah, this is alpha t is something like a function of t's.
Okay.
And usually, I mean, you can think about it, decay functions and those two zeros.
All right.
I thought it was 2, so that would be
No.
complex. Yeah.
I thought it was part of it.
No, it's alpha. Sorry, it's alpha. All right, so let's start with the, and also, okay, so yeah, and before we move forward, so like if we have this Q5 and then like this way, so the only parameter that we have is alpha now. So basically there will be no parameter and for the phi right here, just using the alpha t to control the mean and the variances directly. Okay, so now the question is why this has to be like this, right? So let's, and we know we want to like tear down the images with the linear form, but the most general linear form is like this. Plus beta t epsilon. Right? So now this alpha t and the beta t, you can think about it independently. But let's do it one by one. So we can do alpha t, then we keep substituting this. This is alpha t minus 1, t minus 2, plus beta t minus 1, like this, plus beta t. So if you continue to do this, you can plug in this iteratively. You are getting this alpha t minus 1, alpha 0, of alpha 1 of x0 plus bunch of terms with respect to epsilon. So we have alpha t, alpha 2, beta 1, epsilon 1, plus alpha t to alpha 3, beta 2, epsilon 2, plus the last one will be beta t and epsilon. And in this case, all these epsilon I are, ID, because we example this and epsilon independently and follows the standard Gaussian distributions. All right. Okay, so we know this is all contribution from noises. Let's just call this gigantic terms equal to W. And so we know this, and this is the part that we just multiply the constants on x0. But then we're adding some gigantic, complicated noise term. So, and to quantify these noise terms, we can use the covariances of my WT's quantifier. And we know xi and xj are independent if I is not, so, and that means the covariance of epsilon I and epsilon j should be 0 if I is not equal to j. So we only have the square terms. Plus t3 square terms. By the end, you are getting alpha t squared beta t plus beta t squared. So you can see this is quite complicated. The form is very complicated. So that's why things start to And it makes sense if my and my alpha t squared plus beta t squared is equal to 1, which is my case is right here. Right, because we know this is my case, right? If my alpha, so sorry, my, so like here, my, and this whole thing will be my alpha t. So if this whole thing squared, plus this whole thing and a square, that should, I mean, so and equal to 1. So this is the cases. Then for all the t, right here, then can be further simplified. Because everything here will be the same, but the last one will be like this. All right, you factor out 1 over plus 1 minus alpha t squared. Then this whole thing becomes and I'm going to factor out one more term, square beta e minus 2 square plus alpha t squared beta minus 1 plus 1. So we know this will be, where's the razor here? This becomes minus alpha t minus 1. So then these two things can still combine, you're getting beta t minus 2 squared minus 1. Gradually, you can strip out and substitute this beta t squared, beta t minus 1 squared, beta t minus 2 squared until you get the beta 1 squared. So at the end, you are getting something like this. And you are and lastly, you're going to substitute beta 1 by 1 minus of alpha 1. Then this becomes 1 minus of alpha t alpha 1. So the reason that we choose my tiered down process like that is because the covariance of the noises of this iterative formation can be simplified. Otherwise, it cannot be simplified. Okay, so then what we do is we define my alpha t bar is my multiplications. One, I think I'm not sure whether that's a good idea to call the square root of alpha t because that's getting things more complicated. Okay. Yeah, maybe we can redefine things a little bit. Well, then we can simplify this whole thing, which is alpha t bar x0 of beta t bar of tips. And so basically, so for this noise part, I mean, as far as the covariance is matches, that will be fine because I mean, and this whole part and noise part is like random variable anyway. So I mean, so these two things are the same. I mean, in terms of distributions. All right, so So that means we actually know everything here. Let me think whether I should do it with okay, let me just call it alpha. I think it's a bad idea to call it square root. Then this becomes 1 minus alpha t squared, right? So this will be alpha t. There are like different notations, but I mean, it should be consistent. Okay, so basically we know everything for this phi theta. If you are given this alpha t, then you know the mean, you know the variances. Then the only thing that you need to learn is this like theta right here, which is you given xt minus 1, you want to compute a model for x. Okay, so this whole thing up to now it's still fairly straightforward. For the next couple, like 10 minutes or 15 minutes, I'm going to skip some derivations. A lot of derivation that I'm going to show here will be very tedious, but I will give you some answers of the why this will be doing this. Okay, so how to train this whole thing, like p theta, that means xt, at a condition of xt minus. So this is not an easy task. So we need to step back to use the same trick. The same trick that we use in BAE, that means I'm going to using output again. It's evidence lower bound. So let's go back to this logarithm of likelihood of x here, which we don't know the px and px0 at all, but we can marginalize it with all these latent variables from 1 to t. And so this is basically definition of the marginal populations. Then what I'm going to do is I'm going to multiply by condition of x0 divided by condition of x0. Same thing, just multiply the same thing, top and bottom. Then what you can think about it, I mean, this is actually a distribution, right? So probabilities of x1 to the t conditional on x0. So this becomes by definition of expectation with respect to this distributions of log of p of x0. So this whole thing is very similar to what we did in BAE. But the difference is we are not just have a one like latent variable. We have many latent variables from x1 to x2. Okay, so I'm not going to go through the derivation again, but this is bigger equal than. And so basically the way to think about it is I'm going to, sorry, I think I missed the log, and there's no log here. So basically, I want to switch the logarithm and expectations. So if we switch that, that will be bigger than equals. This is guaranteed by the Jensen's inequality. Logarithm. Okay, so this is basically my elbow. But the beauty of everything is this elbow can be decomposed into multiple parts, like what we did in BAE. I want to remind you, in BAE, we have a two-part that we actually decompose. One will be the prior matchings, one will be the reconstruction areas. This, we know, and not only we have these 2 points, because in BAE, we only have a one, like, annihilation variable, which is the Z. But here we have basically T minus, and T minus, well, 1, so different, like, and random variables. Sorry, annihilation variables. So with some algebra, so this is the key. I mean, I'm not going to show the algebra. But the key is this elbow have 3 parts. The first part is called like this. If you go back to check what we did in BAE, this is very, very similar to something called reconstruction. Called reconstruction. Then minus of KL divergence of xt conditional on xt minus 1 and P of xt. So this is prior matching. The third term is the new terms. Is summation of t from 1 to negative t minus 1 of q xt minus 1 t plus 1 of x of KL divergence. Right. So, wait, is it Q P theta t plus 1? Okay. P minus 1. Okay, P theta. P mean. If you just using the and replace this by the sorry, I think if you're using this P right here, but this is actually you have to using the and base rules and flip back. So and substitute this and a theta and a parameter there. So this is a new term. So this new term is called consistency terms. These two things are pretty straightforward. I mean, in fact, this, and you don't, I mean, even need to learn this prior matrix because we know at the end, this is a white noise. That means and white noise right here, this is already known. So this is already fixed. If you are given the and a phi of t, this is already fixed. So basically, this KL divergence of this to this is basically constant. And of course, this one is, and it's, I mean, it's different, but and we still need to learn that. This one is the problems. It basically says I want to sample for given you need to sample xt minus 1 and xt plus 1, which is okay. You can do it. But the tricky thing is then use xt minus 1 and xt plus 1 to sample xt here. And right here, we still need xt. And to calculate the KL divergence of these two things. This is not very natural. So so somehow you want to, an example, the one, like step 1 further and a step 1 back. And example the things in the middle. All right, so this is not very ideal here. And also, we know this will be p theta of xt minus 1 of xt. That will be the function we're trying to approximate. But here we have xt conditional on xt minus 1. So basically, we need to using the base rules to flip the conditional probability, which is not easy at all. So these whole things, and it makes this consistency terms extraordinarily difficult. So here is the trick. The trick is going to be the following. So instead of we are interested in like probability q of xt conditional on and xt minus 1. I'm going to condition everything into x0. So basically, I mean, since we know the x0, we can take advantage of this. So we know this is q of x. So basically, the key is, I don't want to do the KL divergence of these two. I want to do some more unconditional on x0. Turns out this is much easier. So once we condition on 0, we can make things a lot easier. Because this elbow can be written as follows. Same elbow. Has 3 terms. The first term is being the same. Second term. Well, I mean, it doesn't matter here because this is still not going to change anything. Minus 1 and x. So this is optics. Doesn't matter. The third terms. The key part is the third terms. Becomes smaller. Turns out we don't need the t minus 1 and t plus 1. We can write everything like this. It will be much, much natural to be dealing with. is basically this is consistency. So and what does that I'm actually doing is you can still have the same diagram that we have. This is tear down process. And we know this is the reconstruction, review the process. And also this one. The key part is I'm going to calculate using this tear down process to calculate a probability of Q phi of xt minus 1, conditional on xt plus 1, sorry, xt, and x0. So what does that mean? I used the tear down process to build a model of Q theta. And in return, because I know everything basically, then I can actually calculate the top probability right here. I'm using this top priority and a top probability. I want to match the probability of b theta xt minus 1 conditional on xt. If these two probabilities are close enough, that means we train this theta good enough. So this is very unnatural part. In fact, many people already to go through all this algebra is really, really tedious. But the most fundamental part is right here, is we want to approximate this p theta. But of course, we didn't know the true p xt minus 1 and conditional xt. I'm using this one as a proxy, right, to make sure these two things can be as close as possible. So basically, using this thing to construct and the reverse transitions, then we match them. So this is exactly the denoising part. It's called denoising matches. That turns out to be the most important part in DDPM. If we can understand that part, then we are ready to calculate. Okay, so first thing first, what is this P5 right here? This term. Right, so we know this is the Gaussian because Q5 is always a Gaussian. Like we are just doing some like linear transformation plus some kind of Gaussian noises. By the end of the day, it's like manipulate in a linear transformation of some Gaussians. We know this is a Gaussian, but like, and what kind of Gaussian it is? Right, so the question lies in the following.
Sorry.
Yeah. Yeah.
What exactly are your assumptions? Like there's some sort of
So are you talking about P and P1, P and P5?
So P and Q are
Unknown.
yeah. So you seem that that's like talking about this paradigm build up.
Yes. So this is the model. So basically, model. So like the model, like specify my Q basically this Q looks like that. Because through this like tear down process, I know precisely what is my Q. Right? But we still don't know the P at all, because the P is something that we want to learn. Like once we using tear down to get the like x0, x1 to xt, these are my training data. I'm using this data to learn the P theta, basically. That's the whole idea.
So you didn't think of.
Yeah, basically we know the Q because we have this model right here. Right? I mean, this is basically, so you think about ground truth. You basically tear down at each level, so you know precisely, and this is a Gaussian distributions. Here is something we need to figure out gradually. I haven't like touched that, but we can, and by the end we are going to assume this P theta right here is also a Gaussian. But we are going to using this like reparametrization trick. So basically, yes, this is a Gaussian. But this is the mean is function of an xt plus 1, which is a parameter of the theta. That and the mean is the part that we're trying to approximate with the neural networks, and also sigma. Sort of like BAE. Yes. Yeah. But it's like sort of like Q, but it's like reversed. It's like different in the directions. Right. But I mean,
So when I guess theta is being learned.
Yeah.
Oh, what is the loss that is getting reduced?
or that I'm going to derive soon. Here we have theta here, right? We have theta, that will be the loss that we're trying to derive. All right, so first thing first, what is Q QXT minus 1 condition on XT and X0. And you can put phi or not, doesn't matter, because we know this is a ground truth. We know this is a Gaussian because we're just doing a linear transformation of a bunch of Gaussian. It will be a Gaussian. I know this will be a random variable of xt minus 1 conditional on some linear combinations, which is A, I'm going to call A of xt plus B of x0 plus of sigma q. Right, so this is something like this.
So it's phi, straightforwardly dependent on the alphas.
Just so you can think about phi as alpha.
Okay, phi is
Yeah. Okay. Yeah, phi is alpha.
so we're posing a problem in which basically the alphas are what's given.
Yes. Okay. Okay, so that turns out this question is so and also we know that xt is equal to square root of I think I called it square root of. Did I call it this way? Yeah. Xt. Yeah, I still call this. I think. Sorry, I think I. So I mean, in my notes I'm still using this one. So I'm going to and still using this one. Sorry. This will be slightly confusing, but hopefully it won't be too much. Okay, so this is known. I mean, this is actually could be a very good and a statistic qualified exam. So basically, you want to know the xt minus 1 conditional on xt and x zeros, and we're given this in the linear and equations. Okay, so how to do that? And let's get rid of this things by using conditional probability. And basically I'm going to flip the order. Right. So
Right, so you, before you changed that formula, so it said xt equals alpha t. Plus that the square root.
yeah, sorry, I
plus
think
alpha.
yes, yeah, that's the same thing, basically the same thing. Just so I think and so the reason I did that because in my notes I'm using this notation, but yeah, I mean, so I realized this like alpha is different from alpha that I previously calculated. So there is like slightly inconsistency. But in the literature, people use this notation. Okay, I mean instead. Okay, so this is each of that will be a Gaussian. So this top one will be Gaussian of basic xt because a condition on xt minus one, so this x0 doesn't matter. This is also a Gaussian. And divided by. So you have three Gaussians. And basically, you multiply these two PEM and divide by the third PEM here. The calculation is pretty tedious. So you basically, I mean, this whole thing is proportional to xt minus square root of alpha t, xt minus 1, squared divided by 2 over 1 minus alpha t, plus xt minus 1 subtract divided by 2 over 1 minus alpha t. And the minus xt okay. Okay, so it's like that. So we know by the end of the day, it will be a function of xt minus 1 of xt and x0. So you want to rewrite this three term into a variable of xt minus 1. So you hypothetically, you want to get of xt minus 1 subtract of a of xt plus b of x0 squared divided by 2 sigma squared. Okay. You are going to massage these three terms, and it becomes the form like this. So this will be your variable. You treat xt and x0 to be a constant because you conditional on that. Then you need to find out a and b and a sigma squared. And of course, that's not easy. I don't think I have time to talk about the trick here. Okay, let's talk a little. So the trick is, it's far. The trick is this. You know this XA, this has a form like this. So you don't know the A, you don't know the B. So the way you do, you take derivative of x, basically, and equal to 0. Then you know this x star will equal to A. So that's how you do it. You know, this is very difficult to solve for quadratic function. The way you do is you put these three and a quadratic function, sum them together. Take derivative with respect to x t minus 1. Then you equal this to 0. Then you can solve this term right here. All right. So if you want to find out the b right here, you take second derivatives. If you take the second derivative, you're getting 1 over b. So that means if you take this whole thing, taking second derivative with respect to xt minus 1, you are getting 1 over sigma squared. Okay, so this is a trick. You don't, actually need to massage these three square terms. You can using this like derivative information to find out this and a, b, and c. Okay. So if you apply this trick, you will find out this a right here will look like this. The b is look like that. So like, and basically this is a is known, this is b is also known. The bar, so x bar is the multiplications of. And also the sigma here, sigma square is so this whole thing, the mean and the variances is completely and determined by an x0 and xt's. So this is determined by x0 and xt's. Okay, so by the end of the day, we need to calculate these two forms, right? This part we already know. We need to learn this part. Okay, so then the next assumption is two. Something we want to learn is a Gaussian. This is a common way that we think about it. The difference is the mean could be complicated. So basically, we use the same idea of the reparametrization trick of mu theta of x of t. I'm going to use the same sigma. Now we're already here and have right here. And this sigma and the variance doesn't matter here. I mean, the variance is just a change of the and the weight. Okay. All right. So then I have a couple more minutes. So this whole thing right here is this part is equal to a KL of normal distributions of t minus 1 conditional on this A and B right here, A of x t plus B of x 0 of this sigma q squared. And right here is my mu theta xt and a sigma q. AL of Gaussian, we know that precisely this is equal to 1/2 sigma q squared of 2 norm of the mean. So I'm going to plot this right here. But this A and B is a function of t as y right here. This is AT xt plus BT x0 subtract the mu theta of xt. Right, so basically this is a network weight. This is basically the true mean. So you want to and tune your neural network, trying to approximate the true means as much as possible. Okay, but of course that's for xt. We also need to sample this xt based on this distributions right here. So basically, my xt has to follow. But this is easy because I can sample my xt equal to like this. We already did that. I think I messed up the notation a little bit. Okay, this epsilon is Gaussian distribution. All right. So sort of we already and finish everything that we already talked about. So and then let's do a little bit summary here and finish all the calculation. And also there will be one more term that we didn't do, and which is so this part right here. So we also want to finish that as well. So this consistency term is the most headache part. This part we don't even need to learn. and this is a constant. This part, we still need to learn that. But that's just a one step. Since we already assume this is the Gaussian, so right here. So log of p theta is actually a Gaussian of x0 conditional on x1 and the sigma q, right? So this is also a function of t, right? And take the logarithm, so this is logarithm. So if we calculate these things, this is proportional equal to minus 1 over 2 sigma q square of 1. I think I'm be sure this is t. You theta x1 minus x0. Right? So this whole thing actually can be matched right here, just for this part. And we don't have any weight, which is, and you can define at t equal to 1. This A1 is just being 0 and B1 is just being 1 right here. So this is a degenerate case. Case of B1 equal to 1 and A1 equal to 0. Okay. All right, so I think that's everything I want to talk about this. I'm going to summarize everything in the next lecture. But that's basically the whole thing. I mean about DDPM. So the key idea of the DDPM is we actually need to write my algo into these three terms, particularly for these terms. If we write down this term in this form, it will be much easier, much easier to be handled. And in particular for this first term, we can actually calculate this analytically. Since we know it's a Gaussian, we know the mean and the covariance is analytical. So then all we need to do is try to match the means. We can write down this loss functions precisely. And also we can write down the loss function for the first term precisely. We combine them together, it becomes the loss function we're going to be using. All right, so this is a little bit messy here, but of course there's a lot of benefit to do in the DDPM. And one of the benefits that we do is we don't need to worry about dimension of hidden variables, and this whole process is it's much easier to process than VAE. It turns out, and in terms of training, that will also be quite easier. And the sampling part is also very good. Just one step you can sample. You don't need to sample xt step by step. You can just sample from x0 to xt in one step, because everything is Gaussian. You can step and then forward from 0 to 2. All right. So that's everything I want to talk about that. In the next lecture, I'm going to summarize everything that we did for the DDPM. Then we're going to work on this format change. All right, that's it. Thanks. Any questions?
Yeah, so when, let's say, the Q is determined by the parameters, and then you calculate the P with way. What objective relating, x0 and xt?
What is
you
objective?
achieve- You achieve when P is determined, like, so the fourth picture, what the goal you want to calculate the P's so that some property is true about this sampling that you're describing, right? What is the property that your conclusion of calculating P? What property does that achieve with respect to the diagram you started at?
So yeah, so the whole idea is P is unknown. We don't know the P yet. And
Well, no. So,
yeah,
you know, well, it's unknown for attaining an objective.
yeah. So
Yeah, so you
so
can make
basically-
an arbitrary
yeah.
P and go around. It
so the
doesn't matter.
objective is this part. Sorry, it's this part right here. So we're trying to train this Gaussian distribution, so mu theta xt. And I want to emphasize this and this whole thing is actually, we're trying to approximate this thing right here. That's the objective we're trying to learn. So basically, the whole idea is we're trying to learn the mean of this P theta as a neural network and
Okay,
using
so-
neural
So
network.
when the learning is completed,
Oh, where is
what
learning?
can you say about the situation
Okay, so
that your
what-
diagram, this diagram?
when the learning is complete, that means we getting really low, say the loss functions for this and elbow here. And by the end of the day, I think I yes is right here. So that means this reverse process, the probability of this reverse process is well approximated by this P theta right here. So this is my kind of proxy probability right here.
Oh, I see.
This and these two are close enough.
Oh.
So these two
the-
are close
the-
enough. That means my theta is good enough.
So given Q.
Yeah.
The conditional distribution that you wrote in blue
Yeah,
is determined.
it's yes.
It's determined by
By the P.
the universe.
Yeah.
And your goal is to get a computationally effective approximation.
Yes.
Okay.
By using this by using the theta,
Yeah.
because like, and this whole thing is like an independent of x0 right here. So like once I know xt, I can go back.
Okay.
And from xt to xt minus 1. But this one, like we cannot go back because we know the ground truth. That's impossible. Right? I would want to generate images,
Oh.
right? But
So.
during training, we know this part. So then that means we want to train this whole thing that to be as close to this thing.
So platonically, that Q, that distribution denoted by Q exists.
Yeah.
But you don't have any information about it because you've only trained on a few of the possible values of x0.
Mhm.
There's no way you have a formula.
Yeah, I don't have problem.
So if someone comes in with a new value of x0.
Yeah.
You can't really get this without carrying out the process.
So basically, I mean, so if you have a new x0 or something like that, but like on the bottom part, I will talk about in the next lecture. So with the hand of the bottom part, you can actually propagate from x capital T, x like capital T minus 1 until I'm x0.
So with the bottom part, after you train theta.
Yeah.
Someone hands you a new x0, you could just calculate the
Yeah.
p thetas.
Yeah, that's the training part. Yeah.
And then after, when you give it an x0, you can find the p theta, and that will be a good approximation to
Yes.
the value of Q for that training set.
That's the training example. Yes, that's for the training.
In practice, do you use this to generate images from something?
Yeah, from the like and white noises.
Yeah. Is it also, we have like partially noisy image to try to construct that? Or
Yeah, you can do that, but like,
that's not the main purpose?
but that's not the main purpose. Like denoising is not the main purpose.
Yeah, I know it just says not the main purpose, but as someone who's not a data scientist, can you kind of describe deterministically like what the process, because I'm almost I don't think this does denoising, but I'm almost thinking like you start with an image, you FFT it, throw out some coefficients, add some noise, keep reproducing that
Yes,
until
you
you
can do
throw
that.
out,
Yeah.
out so much that all you're left with is white noise, and now you want to kind of,
Yes.
is
So,
that
yeah.
sort of like
yes,
what
but the issue
deterministically?
is from, I mean, if you have
Oh, sorry, I meant FFT, throw stuff
Yeah.
out, then inverse FFT
So
again.
then you have like a noisy image, right?
Yeah,
First things is if you do this way, this is not like white noise like here. That's a different way of and it's tear down the images, right? At a throw away and high frequencies, then you like re-inverse back. That's not the same tear down process I did. That's a different one. That's the first thing. But of course, you can still put this right here to go back, but that's no longer being denoising because I mean, if you go back this way, it might create like, and based on the thing that you had to create a new image, like and say like, and suddenly and you have like an additional hand or like additional feet coming out of this image without any notices here. So that's denoising is generating an image is like two different tasks because you want to, and the denoising part, you want to make sure you're and trying to match the original image as much as possible.
well, so that's the question, can you like describe even like the crudest way to do it, how would it work on deterministically X0 to X1?
That's not the main goal. So I don't think that's
Right.
like at the part that you can.
I understand.
Yeah, but you can like throw this in, but yes, you can generate this and from XT to X0 with a noisy image that you already have. But it will no guarantee you can get the original image back.
So I guess it's the main goal that you train, you pick, you have a training set of XUA. Get the I don't know, some average.
So you want to,
For the parameter, you've determined the thetas.
yeah,
And then the punchline is that when you input a true sample from white noise
yeah,
as XT, you get an image under a distribution. That if you get image with really random XTs, you get output images whose distribution is approximately the distribution that the
of X0.
that the training one
Yeah.
that you're on from.
Yeah. That's
So if you train it on cats,
yeah,
you put in a random, a real random input. You will, if you're successful, you'll see something that looks like a cat.
yes, yeah,
I see.
yeah.
So
So
it will be a cat that no one has ever seen before.
yeah. So basically, the whole idea is I want to sample X0
Yeah.
following the training data set you already have.
I see. So it's like it's used in these things that create art.
Yes,
Okay.
So this is like the main thing that's used for.
that has been used. I mean, that's a like a backbone in the ChatGPT and the DALL-E and all these kind of things.
Okay.
But
What's a range of examples, including ones that are less motivated by simple fun?
okay, so like there will be more things can be done. I mean, so in the next lecture, I'm going to talk about and the one score basis coming up. There will be more interesting things too. Yeah, okay, so this whole thing is no longer used like because in order to get from XT to and back to X0, this T has to be like I think 1,000 or 2,000 steps. Really slow. That means I mean if you want to generate a cat from like and after training, that you actually have to wait really long time to see a cat to show up. But nowadays, if you ask ChatGPT, okay, create an image of cat, it will come out within like 1 second or half second. So there are like new techniques, new things to improve this whole process. Yeah. They even have a connection to the first lecture I have talked about and related to stochastic differential equation. I haven't even touched it yet. This is the part that you need to learn SDE. Everything right here is still discrete. I'm going to continuarize everything, and then becomes an SDE, then everything becomes like mathematically really beautiful.
So I guess obviously,
if you ask ChatGPT to create a cat,
yeah,
ChatGPT has been trained on a lot wider range of images than cats.
Yes. So you can think about this.
As it knows how to classify cats.
Yeah.
Okay.
Because data that ChatGPT of all these large language models, it's not exactly this way, but you can think and about what and during training they have seen enough things that they can recreate these things and automatically. Yeah.
I'm just getting back to my question. In practice, can you literally just algorithmically do XT is the square root of blah, and then just that is literally the denoising process, or is that just the model?
It's just the denoising process. You can do it.
But that is the process. It's not just a model for the process.
So I'm going to talk about in the next lecture how this is being done.
Okay.
But the key here is that's different from denoising the image, because denoising image you want to make sure you recover the image. But this whole denoising thing is you want to generate an image.
Okay.
But if you input a noisy image back, you might getting some images might be close to what you have, but like suddenly there will be one more hand coming out of that. Okay, so you get what I'm saying?
Yeah, another probably silly question.
It's not an effective method to, the old-fashioned, which photography software that denoises images. This is not a good method where you take the noisy image, you run it through this sampling system, take the output, and then process it with the cues. That doesn't really work very well.
Yeah.
Okay.
Now, while you're racing, is there a reason you couldn't just solve for X, or what goes wrong just solving for XT-1 and just getting distribution there, knowing XT? So just subtract.
You mean this one? This one?
Above. So yeah, where XT is square root of, just literally subtract and divide by, sorry.
You mean this one or this one?
Right where it says known?
No. Oh, no, okay, this one. Okay, this one.
Yeah, so is there a reason you just couldn't solve for XT-1 because they're given XT?
Yeah, XT and X0. So because that's the future and the past. You given the future and the past, you want to know the distribution like intermediate.
Right, but if you know XT-1, I mean, you're taking, I guess, 1 over a Gaussian. That might be weird, but
no, because you condition on X0 and XT.
Oh no, it's not 1 over.
It's not. It's not 1 over.
So yeah, it's right.
That is one of very classified and one of its very classic statistical problems. And basically condition on the future and the past and what is the and the distribution of the current.
Right, but I'm saying if you like you know XT-1, so then you can get.
But you don't know that. In fact. I mean,
okay.
I mean, if you write this way, is you know XT, you know X0, you don't know X and T-.
Okay.
Okay.
No, sorry, I meant you know XT. So
I
then,
know XT in this formula.
Yeah.
But in this formula, I know XT and X0. I don't know what is XT-.
Sure.
But I only know this like an iterative formula.
Okay.
Okay.
Yeah.
All right. So more in the next lectures. Sure. All right.